This video is going to show you how to sketch graphs of derivatives. So you can do first, second, third derivatives. You can go as far as you like, really, until you get to the point where you can't differentiate anymore. It's a really handy skill to have because it really helps you visualize what's going on with your derivatives, and particularly when you start looking at applications. So say to displacement, velocity, and acceleration. It's really good to have that visual understanding of what's actually happening to the particle or whatever it is that you're looking at. Okay, it'll also help you with sketching graphs in general, which we'll look at a little bit later. So let's get stuck into it. So we know that the derivative of a cubic is a quadratic, okay, because we know that if we have f of x is x cubed, then we know that when we differentiate that, we get 3x squared. Okay, and we know that if we differentiate that again, then we're going to get a linear equation, and if we differentiate that again, then we get a constant value. Okay, and if you do that again, then you just get 0. So you can see that each time you're dropping down. So what does that actually look like in terms of practical sort of visual representation? Okay, so if we start with this one, this is our cubic. Okay, now if we want to sketch this, we know this is going to be quadratic, but the important things to note are your turning points, because remember, this is the gradient. This will show the gradient of the cubic. So when you have a turning point, the gradient is 0. So at this point, the gradient is 0 here, and also at this point, the gradient is 0. So if it helps, you can actually drop yourself a little dashed line down there. That's why it's really good to do these one under the other. Alright, so that's going to be at point A, and that's going to be at point, not B, C. Okay. Now, this is where it starts to get a little bit confusing. What you've got to look at is, what is the gradient here? Is it positive or negative? So it's sloping up, so it's a positive gradient, therefore it must be up here, above the x-axis. Okay, so it has to be like this. Now this is where it confuses people, because people look at that and go, but that's negative because it's a negative gradient. But we're not looking at the gradient of this at this point, we're looking at the value. This is a positive value. Okay, between here and here, you have a negative gradient, so that must be below the x-axis. And we know that it's going to turn around somewhere, go back up, and then from here to here we're back to positive, so it's a positive gradient. And what this means is that this is a very positive gradient, high positive value. It's getting less positive or less steep down to here where it suddenly has no gradient, so that's as you curve off to this flat point here, and then negative and turning around. This point here, where you've got a turning point, this is your point of inflection, where your concavity changes from concave down to concave up. So it's sort of about there, I think. Alright, so that becomes an important point as well. Okay. Now the next one we're going to be looking at is the gradient of the parabola, the quadratic, but also the concavity of the cubic. So now it's telling us two things. Okay, so again we sort of take a similar approach. If we're looking at the gradient of the quadratic, the gradient here is 0, so that's going to mean by 0 point. Okay, the gradient on this side is negative, alright, so it's going to be below the x-axis, and on this side is positive, so that's going to give us a straight line. Whoops. We know it's a straight line, because we know we go from quadratic to linear. Okay, and then the last one, we're now looking at the gradient of a straight line. Now that's just constant, so it's positive gradient sloping up, so this is just going to be a constant there. Okay, so this is now the gradient of the linear function. Alright, so hopefully you can see the relationship as we go from first derivative, second derivative, third derivative, and how that relates between the three. Alright, so you're always looking for stationary points, so find your stationary points, they will represent a 0, so an x-intercept on the derivative function. Okay, and then this one, stationary point, that then drops down to here. Alright, so the way we read this is positive gradient of the cubic and negative gradient of the cubic, so between there. This is concavity of the cubic, so this means we've got concave down, so if it's negative it's concave down, so between there and there. And then when it's positive, it's concave up. Alright, so down here is concave down, and up here is concave up. Now, it does take a little bit of practice getting used to switching between and sort of trying to separate the idea of positive and negative gradient from the previous graph as to positive and negative gradient on this graph. Okay, so a little bit of practice on this and sketching them, but it's a really, really handy tool to have in your toolbox, so do make sure you practice. Alright, so let's have a look at a couple of examples. So the first one, we want to look at the gradient. It's a linear function, so it's going to be a constant. Alright, we know it's a negative gradient. The gradient's -1. Okay, so it's just going to be a constant value of -1. Alright, that's the derivative function there. Here we've got a cubic, well, sort of, looks a bit like a cubic, a point of zero gradient. Okay, so that's like an inflection point, but it does mean that it's a stationary point. So it's a stationary point. So zero gradient, that means that there's zero gradient here. Now, if we have a look at what's going on with the gradient on either side, this is positive, okay, and then it flattens off, but then it keeps going on positive. So this does not drop down below the x-axis. So what that means is you have a quadratic which comes down here, touches there for a zero gradient, but stays positive, doesn't go below. Okay, so that's how we represent that one. And then this one, we don't have a flat spot, we don't have a stationary point. We do have a place where, so we've got steep gradient, it gets less steep to a sort of a minimum steepness, minimum slope, and then gets steeper again. Okay, so what that means is that it comes down to a minimum gradient here, but the minimum gradient is not zero, it's not a stationary point. So it's just the quadratic is somewhere, some value above the x-axis. Doesn't matter where, just you've got to indicate that it's somewhere not sitting on the x-axis. But same thing otherwise. Positive, always staying positive. Okay, so that's positive gradient there, and positive gradient there. Okay, so a quick sketch like that, don't really need any values except for this one where you've got those, but you just need to be able to sketch what's going on and where your stationary points are and how that relates to intercepts on the derivative function. Okay, so we'll talk very briefly about differentiability. We come into this a lot more formally a little bit later in the course. But basically what it means is that some functions may have a point or points where the gradient is not defined, so you can't differentiate it at a point. So you might be able to differentiate the function on the whole, but you find for a certain value or values of x, there isn't a value of the derivative. So a typical example of this would be a piecewise function. Okay, so this is or an absolute value function, but we can define this as a piecewise function. Right, so we might have f of x equals, and we don't have any numbers on here, but we can say it looks like it's negative x for x is less than 0. Okay, and then, or less than or equal to 0. And then positive x for x is greater than 0. Okay, but when we look at doing the derivative of this, okay, we're going to have, we've got a value here, a constant value of the gradient there, but then at this point there is no value because it's not a smooth curve. We can't say that's a stationary point. It hasn't come down into a sort of decreasing gradient and then flattened off. It's actually, it's almost discontinuous, so to speak, in terms of gradient. Okay, so it's really not defined at that point. So what we've got is a negative gradient, and if we've said this is -1, so that means we've got a gradient of -1 over to here, and then at this point it's undefined. Alright, and then up here, this is now +1, but it's still undefined when x equals 0. Okay, so you've got this sort of step function where you don't have a defined gradient. So gradient is undefined. Undefined when x equals 0. Okay, so that's where you get the sort of stepped function. Alright, so an example of this one, draw a sketch graph. Alright, so this is almost exactly the same as the other one. I always find it easy, or easiest, to draw straight underneath, because then you can line everything up. It just makes it that a little bit more straightforward, a bit more visually appealing. Okay, clearly here, if we're going from 1 to 2, we've got a gradient of 2. And coming down again, we've got a gradient of -2. Okay, so that just means up to this point, your gradient's positive, where that's 2, and then down here, it keeps going, and that's -2. Okay, and clearly you could do this with any kind of piecewise or discontinuous sort of function. where this is defined, and you can find the gradient. Okay, so that gives you some idea of just the intro to differentiability and the concept that not all functions are differentiable at all points. But as I said, we'll go into that more formally a little bit later in the course. So in summary for this video, it's really important to understand the relationship between the graphs of a function and its derivatives. So like I said before, probably several times, do practice that. Make sure that you can sketch those relationships, locating your turning points and your points of inflection, and identifying your positive and negative gradients and your concavities up and down. Okay, and keep it clear in your mind which function you're looking at any one time. And the other thing is to recognise that not all functions are differentiable, or at least not at all points. So look for pointy bits. Anytime you've got a pointy bit on a function where it's not a nice smooth curve, it sort of has that abrupt change in gradient, that's a pretty good clue. And also asymptotes, so we'll go into that a little bit later as well.